approaches which we tried at the beginning. Firstly, we wanted to co-polymerize the nanoparticles of titanium dioxide into the monolithic matrix, because the monolith is produced from the monomers. So you polymerize it and you get the final structure of the monolith. So if you add the nanoparticles of titanium dioxide inside, they should be incorporated in the matrix itself. And actually, there were quite some experiments tested, and this is, for example, the CDM picture of one of such monoliths. We were able to obtain the monolith, but with proven titanium dioxide inside the structure, but still it was not a really homogeneous structure, and we then slowly focused more to the other approach of preparation of titanium dioxide monoliths, in the way that we took the monolith as it is and we immobilized the nanoparticles on the surface of the monolith. In this way, getting much higher surface area. This was our expectation, and to have the very stable layer of nanoparticles on the surface of the organic monolith. Indeed, we studied at the beginning different, let's say, activation chemistries, even though they are not really activation chemistries, but we started with two different matrices, and we studied two different structures, crystalline structure of the anatase rutile and the anatase nanoparticles. And with the both, we succeeded then later on to get the layer of nanoparticles on the surface. And with the rutile nanoparticles, it was also, for example, we had to increase a little bit the pore size of the monolith, otherwise the clogging effect was already seen. So that when we took the monoliths with the 2 micrometers pore size, actually we didn't have any problems on the clogging, and we could very easily load the titanium dioxide nanoparticles on the monolith, obtaining the capacities. So the capacities, this means how much of titanium dioxide was absorbed on the surface of the monolith. Let's say somewhere between 20 and 30 milligrams of titanium dioxide per milliliter of the chromatographic color. And then, just to prove that we really succeeded, we did some characterization. This is, for example, IR spectrum. Actually, this is the green one, is the IR spectrum of the pure titanium dioxide, and if you could, this is actually the black one is the matrix, organic matrix, the monolith, and you can see this small increase of the red compared to the black one. This is actually then a proof in this case for the titanium. The titanium dioxide is there. This is the SEM image is of the monolith. This is the monolith before the immobilization. So this is actually, these black holes are pores inside the monolith. This is the titanium dioxide particles which were used. This is the TEM picture. You can see around 100 nanometers long needles. And this is then the SEM image after the immobilization. And you can see this small pod, actually we can say needles. This is actually the titanium dioxide which covered the surface of previously more smooth monolith surface. And even we measured the surface area of the composite material. Before it had around 7.7 square meters per gram. After it is approximately double, and if you calculate this difference, this 7 square meters per gram, and if you know the amount of titanium dioxide, and if you just use simple geometrical equations, and also if you know the surface area of the material itself, which is 170 square meters, it matches. So this increase of the surface area matches the increase of the surface area due to the immobilization of the titanium dioxide. And the last characterization method used was diffractograms. So this is the classical, the rutile diffractogram having this diffraction pattern, and you can see that even on the monolith you keep this diffraction pattern, while on the brain there is no diffraction pattern. So it means that really it was a successful absorption. We also did this because if it is only absorbed, it could be also very easily washed away, the titanium dioxide. So we performed some stability studies, and we can say that we didn't observe any deterioration of the material of the composite after this washing with sodium hydroxide, organic solvent, or HCl. So that the bond between the nanoparticle and the surface is really a strong bond. And this is also the porograms of the pores of the initial material of the monolith, and pores after demobilization and after the stability measurements, or after the regeneration and SIP measurements. And you can see that the pore decrease is due to the lowering of the pore diameter due to the nanoparticles absorption. But then after the regeneration, there is not a big difference. So the titanium dioxide is still there. And this is also, it was proven even with XRD, so before and after regeneration, the titanium dioxide is still on the monolith. And now the chromatographic evaluation of these titanium dioxide columns, because we are, as I said, focused more to preparative purposes, we just wondered what would be the capacity for example, one phosphoprotein. In this case, we took phosphoprotein ovalbumin as a model compound, and we just wanted to test the difference of the absorption due to the titanium dioxide, and to see how much of the ovalbumin could be adsorbed to such titanium dioxide column. And while on blank column, so before demobilization, there is actually no absorption. This is the dead volume. With the titanium dioxide-based column, we got around 4.5 milligrams of ovalbumin absorption per milliliter of the column. What is, for preparatory purposes, for example, is still not enough, but at least we proved that it has quite substantial capacity for this protein. And then we got the peptide samples, phosphorylated and non-phosphorylated peptides. Actually, we don't have MS, so we actually, everything what we did on classical HPLCs with UV detectors. We just wanted to prove that its selectivity for binding the peptides. And on the left figure, we have this titanium dioxide column. On the right figure, we have its blank, so just without titanium dioxide OH column. And after optimization, the binding and dilution conditions, you can see that really on blank column there is no elution at all the peptides. So this one is non-phosphorylated, the black one, MP. This is one phosphorylated two times, I think, this is 2 phosphorylation, 3 phosphorylation, 4 phosphorylation sites. Actually, for all these different peptides, on titanium dioxide column, they were successfully bound to the column, just the non-phosphorylated was not bound. We also checked what are these small fractions in the flow-through, but obviously we don't expect that this is phosphorylated peptides, because we collected them and reapplied to the column, and actually they were again in the flow-through fraction, they were not bound to the column, so we think that this is impurity from the production of the peptide. Just to summarize, we bound the titanium dioxide. Actually, according to the literature, nobody has bound nanoparticles to monolithic material, organic monoliths so far, so obviously this is the first time where this has been successfully done. And what is very nice is that it is a very simple procedure and very cheap procedure, so this could be done in a very easy way. and just we have proven to selectivity for these phosphorylated peptides. The third goal is the synthesis of serum albumin depletion monolithic column. They, again, at the beginning, there were two different strategies. One was that this actually, from the beginning, we decided to take the antibodies for human serum albumin. So this is from the starting position, and the first one was that it could be bound